Welcome back, my little bundles of momentum. We have a short one today. I think this one's gonna be pretty quick because there's only like maybe why is that changing on me? All right, maybe there's only like two different types of questions. I think today is gonna be short and sweet. We're shooting for under 30 minutes. But I think if I really put my mind to it, I can draw it out. So we'll see how that goes. But today, what we're going to be talking about is different ways to represent the changes in momentum. We're going to focus on how can I measure these things. Would I be able to measure these things? Will the measurements I take give me the thing? And I gotta sneak a little bit of math in there. It's just not physics if we don't get to do a little bit of math. So most of your homework is going to be looking at some graphs, some data tables. It's pretty straightforward, I think, but I've lied to you before, so don't take my word for that. But we'll do our best. So let's go ahead and get her done, as the saying goes. Okay, so there's going to be two different ways for us to try and determine the change in momentum. Again, impulse is the fancy physics word for the change in momentum. Remember, momentum is also a vector and it's also p for some reason. So the most straightforward way to measure momentum or a change in momentum is to find the initial momentum and the final momentum and then subtract, right? Change in momentum equals momentum final minus momentum initial. Usually, like most of the time, and I'm not going to try and quantify most, but usually when we're looking at these changes in momentum, we're going to have mass velocity final minus mass velocity initial. Most of the time, when your momentum is changing, it's because of your velocity, and it's not really because of the mass. Very, very rarely does the mass change because it's like you have to hit something. Mass doesn't just spontaneously grow out of other mass, right? You have to hit something, you have to drop something. And those interactions are not necessarily what we're talking about here. We're talking about one thing changing momentum for most of today. So because this mass and this mass are going to be the same mass, one way you can think about your change in momentum is mass times change in velocity. This will get you pretty far. The second way that we can try and analyze a situation to find the impulse is we know that the impulse formula, which is, again, change in momentum, is force average times change in time. So if we know how much force we're applying to something and how much time that force is being applied for, then we can look at a force as a function of time graph. And then what we're looking for is this area underneath the graph. The area of this thing will tell us the change in momentum or the impulse acting on the system. So that's kind of our goal here. Cool. So let's go look at some examples. Okay. This one's so fun. I like this one. So your friend just got a slick Tronda Bivik, the hatchback sport type Z. He paid extra for that. Or she could buy a car too. And claims that it can go 0 to 60. The 0 to 60 is miles an hour. It's how long it takes to go from 0 to 60 miles an hour. Has a 0 to 60 time of 5.4 seconds. The type Z has a mass of 1,700 kilograms. What is the change in momentum of the car as it accelerates? And we're going to take this a step farther and we're going to analyze what is the average force of friction from the road on the car. So, all right, so let's look at these two types. This question, right? So we've got our type Z. So we've got, what do type Z's look like? Something like that. It looks, yeah. There you go. Type Z. It's spoilers of Z. How tight would that be? Okay, so here's your car. And this thing is going to be cruising. It's going to go from a standstill. It's going to go that way. And at the end, our final velocity is going to be 26.5 meters per second, give or take. It's not exact, but we'll hand wave a little. Because we're starting at 0, velocity initial equals 0. And the change in momentum that we're looking for here is just going to be mass times change in velocity. So to find our change in momentum, it's going to be our mass of 1,700 kilograms. Change in velocity is final minus initial, so 26.5. And then we go find our calculator, and we use that calculator to multiply 1,700 times 26.5. And we get that our change in momentum is equal to 45,050 kilograms meters per second. So there's our change in momentum. That's pretty straightforward. So as long as we know the mass of the object in question, and then the final and initial velocities, we can just go ahead and brute force calculate it, throw it into the momentum equation, and let that thing rip. So now we want to know, what is the average force of friction from the road onto the car? So let's start by just taking a peek at the force diagram in case there's anything weird, but we should just check. So for our force diagram, we've got the weight of the car, we've got the normal force, and then what propels the car forward? The wheels, Mr. Barton. All right, the wheels, but what's the force on the wheels? Well, the wheels are trying to spin, but they're in contact with this rough road, so they can't spin because of friction. So friction is going to point forward for us. So friction is the force causing the change in momentum on our car. So lucky for us, the impulse on an object is also equal to force average. Sorry, I don't know why I put a delta there. Force average times delta t. So we know the impulse. We have 45,050 equals force times time. Our time is 5.4 seconds. So we just plug that in. So 45,050 equals F times 5.4 seconds. And then we can divide by 5.4. And we can get an average force, which is our frictional force, because that's the thing giving us more momentum, is going to be 8,342.6 newtons, because it's a force. So very fun. We can find our change in momentum by just knowing how fast it starts, how fast it goes at the end, and how long it takes. You could do this in your own car. You have a speedometer built right into the car. You have a stopwatch built right into your phone. Hand your phone to someone in the passenger seat, and then as soon as the light turns green, they start it. And then you bwap, bwap. And then once you're done bwap, bwap, you just say time when you hit 60 miles an hour. And then you can calculate this for yourself. The one hang-up you might come across is the mass of your car. You can usually Google it, but if you've got a bunch of weird stuff in your car, like you took out the seats that came in your car and you put in those like fancy wop wop racing seats, you might have changed the mass a little bit, but you could get a good estimate. So fun question. Yeah. You know what would be interesting is knowing so for friction is mu n. mu for rubber and ground is usually like 1.3 or so. We'd want to check the normal force to see if this friction is even possible, right? Maybe your car doesn't have enough friction to get to this. Wouldn't that be crazy? It's like, well, I need this much friction, but because my car doesn't weigh enough, I can't get a big enough normal force, or my tires aren't sticky enough. That'd be an interesting problem. But anyway, so we did our job here. We can move on. We found the impulse, and we figured out how much force the tires are going to feel from the road. All right. So this is an example of just doing it the brute force way by looking at change in velocity and knowing the mass. Now we're going to look at an example of force times time. And we're going to try and figure out the impulse applied to this object. So we have a mass, and it's attached to a string with a tensile strength of 8 newtons, meaning the string will break at 8 newtons of tension. This is like you buy some string from the store and it says 10 newton strength or 8 newton strength. So once it goes past that, it'll break. Usually you can find like fishing line that has like 100 or 200 pound tensile strength. That's so that you can reel in like real big fish and stuff. But like fishing string has this number just printed right on the box. So the mass is being pulled by a string as the tension is gradually increased until the string snaps. Find the impulse on the mass by the string. So we don't know the mass, right? This could be a tiny little paper clip. It could be a big old box. It could be a dog. It could be a fish. It could be your grandmother. It could be anything made of matter. So we've got a mass attached to a string that's going to break at 8 newtons. And then we got to find the impulse. So we cannot use the mass velocity approach here. We have no information about mass. We don't know, is the object at rest initially? Is it moving initially? We have no idea. All we know is that the string is pulling on it until it breaks. So here is a graph of the force as a function of time acting on this mass. So what we want to do to find the impulse, we're going to take advantage of the fact that impulse is equal to force times time. And we're going to find the area underneath this graph. So it starts at 0. At 2 seconds, it starts increasing linearly up to 8 newtons of force. And then at 8 newtons of force, because we've hit the tensile strength of our string, the string snaps. And if the string snaps, it's not applying any more force. So it just drops down to 0 immediately. Maybe on the other end of our string, we have a force gauge to get this. So the situation we're looking at is a mass with a string. And then on the end of the string, we've hooked this thing up to a little force gauge to get this graph. Now, to analyze the impulse, all we need to know is the area underneath this graph. So lucky for us, we went to elementary school, and we know that the area of a triangle is equal to 1/2 the base times the height. The base of this goes from 2 to 6. So this is 4 seconds wide. And then the height of this, we go from 0 to 8. So this is 8 tall. So the area is 1/2 times our force of 8 times our time of 4. And this equals 16 Newton seconds. This is a different unit than we saw in the last problem. And usually, if we're using impulse and we're talking about the force time method, the units of force are newtons. The units of time are seconds. So usually, if you're using these units, you're talking about the force time approach for finding impulse. That might be handy on your AP test. If they give you some multiple choice questions Like they say 8 Newton seconds, 16 Newton seconds, 24 Newton seconds, 0 Newton seconds, just to throw you off. The fact that they're telling you units of Newton seconds kind of tip you off to which method for the momentum that they're using to do the problem. So there are kind of built-in hints. That being said, I know that the AP test writers are also masochists, so they might use the other units that we saw back here, kilograms meters per second, to throw you off. But, if you see Newton seconds, you go, oh, Newton seconds. That's momentum, force times time. So that's a pretty easy question. Really, you just have to realize impulse. I'm using the force times time because I don't know jack about mass or velocity. And then you look at this graph and hopefully you remember the area of a triangle. So I think you have like 2 or 3 of these on your homework. And the approach is all pretty much the same. You find the area, and then that will tell you the impulse. And then if they ask you something about velocity, now that you know the impulse, you could set that equal to mass times delta V. And then you could try and find your velocity from there, assuming they're kind enough to tell you the mass. Maybe they tell you the change in velocity and you have to guess the mass. That would be cool too. So, there we go. All right, let's talk about one more problem, and then I'll send you on your way, and you can go enjoy those beautifully written AP questions. I don't think they're too bad. Hopefully they're not too bad. That's all I'm gonna say. But all right, we have a ball with a mass of 100 grams, and it's spinning on a string in a horizontal circle. The radius of the circle is 60 centimeters, and it takes about 1.2 seconds to make a full rotation. What is the change in momentum after a circle? Change in momentum of a circle after one full rotation. I might have worded this a little weird. What is the change in momentum? We want to know not of a circle, of the ball. Sorry, I've got a little brain fart when I was writing this. So we want to know what's the change in momentum of the ball after a full rotation when it goes in a circle. So let's draw a little picture just so we know what we're talking about. Here's you. And you're doing that thing you love. You're spinning. You got your ball spinning around in a circle. The radius of this circle is 60 centimeters. 60 centimeters. This thing has a mass of, I'm going to put it as 0.1 kilograms. It says 100 grams, but, kilograms, because kilograms, meters per second, and all that good stuff. Kilograms is the SI unit, so I like the SI units. I should probably turn this into 0.6 meters then. And then the time, or the period of rotation, one full circle, is 1.2 seconds. So here's the situation. Back in the good old days when people didn't have TikTok and TV and Netflix and anime and manga and books and stuff, and you were just some kid living on your dad's farm in the middle of the woods, and you worked 27 hours a day, 8 days a week, and then hopefully your cow lived through the winter so that you guys would live through the winter. And you're like, you know what? I'm tired of working. I'm going to treat myself. And then you grab a rock and tie it to some string, and then you'd spin it in a circle. And you go, haha, this is the happiest I've been in years. Right? So we want to know, what is the change in momentum of this thing once it goes in a full circle? It goes all the way around, and now it's coming back, and it's there again. Okay, let's look at maybe a top-down view of our situation here. Here's our circle, and then here is our ball. Okay. This question is a trick question. Let me just start by telling you it's a trick question. Okay. When we have our ball going in a circle, let's say I'm looking down on it and the ball is spinning this way. So my ball is going to have a velocity in that direction. Okay. Then the ball goes around. As it goes around, its velocity is going to be turning and changing the whole time. It's always going tangent to the circle. Once it gets back here, its velocity is this again. So if I want to know the change in momentum, I'm looking for the mass times the change in velocity. And we're looking at velocity final minus velocity initial for the change in velocity. The mass of this thing's not going to change. As I spin my rock on the string, the rock doesn't change how big it is, right? So at the beginning, my velocity is, let's call this 1 for the, it's not 1. We could calculate it using these numbers, but let's pretend it's 1 velocity of velocity. Okay. It goes around, it's still going 1, maybe -1 because it's going the opposite direction. -1 in the other axis. Then it comes back, and the final velocity is the same as the initial velocity, as long as I'm spinning it in a constant uniform circular motion. So my mass times v final of 1 minus v initial of 1, because it ends and begins in the same spot and is going the same speed, there is no change in velocity. Yes, the velocity changed a whole bunch, but because we're looking for change in momentum of 2 specific points after a full rotation, we only care about the beginning and the end, which I think is the most uncomfortable part of this, right? It's like when at the very beginning of the class, it's uncomfortable for us to say if you run around the track at school, your displacement is 0 once you finish 1 lap, because you just did a whole bunch of effort and huffing and puffing to run 400 meters of distance, right? But because distance is a scalar and displacement is a vector, the direction of where you start and finish matters, right? So because we start and finish with the same amount, this is 0. And 0 times any number is 0. So we have 0 impulse when we compare, when we look at one full circle. So they will definitely try and trick you with these funky ones. Maybe not on the homework. I don't know if the homework has any trick ones like this. Maybe it does. I forget. But on the AP test, this is something we should definitely be aware of. And just keep in mind that we are, again, looking at vectors, and the direction of these vectors matters. So because our velocity is the same at the beginning and the end, the change in velocity is 0, and our impulse is 0. If we looked at like a graph of impulse, let's look at a graph of impulse, right? Here's our impulse as a function of time. Here's the end of the full circle. Our impulse would probably look something like that, right? It's going to increase until I'm here, where I have lost all of this velocity and now it's in the completely opposite direction. This is my maximum impulse. Once it starts coming back around, though, it starts getting closer to being what we started with, and we lose some of that impulse again. So yeah, it's a confusing thing, but be aware. Okay, so hopefully these 3 examples have taught you something about measuring impulse. To kind of sum it up, we want to look at either the change in velocity if we know the mass. If they don't give us any information about mass and velocity, then we're going to need to know information about force and time. And then we can use a force as a function of time graph, look at the area underneath it to find our impulse. And then if we really felt like it, we could take that stuff, and if they decide to be nice and give us the mass later, then we could find our change in velocity. Okay. Lastly, we just want to be careful that our starting and ending velocities are not the same velocity, because if they are, then there was no impulse, even if we did a lot of turning and moving and forces being unbalanced and stuff. But if the beginning and end are the same spot with the same velocity, then we might not have any impulse. So if you have any questions, be sure to let me know. Send me an email, write me a strongly worded letter, and slip it in my mailbox. I don't know. Make your own YouTube video. Be like, Mr. Barton, you're terrible. My top 10 least favorite things Mr. Barton's ever said. Until then, have a wonderful day. I'll catch you guys next time.